Hey, everyone. So I'm going to be talking to you again today about math, and I'm specifically going to be talking to you about a function that I have created called the geometry awareness function. And this function is very straightforward in what it does, in that you feed it an input like you would a normal LM model or a neural network, and then it decides what geometric realm that the data should be encoded into, either Euclidean, hyperbolic, spherical, or fractal. And that's really all it does. And then so in the first block here, I have a test of it, and then I tested, I want to train this neural network, right? So this neural network that I've created that essentially is this geometry detector. I want to train it, and you can see here in my training, it took to this data, right? So at first it was like 35% accuracy, and then after 10 epochs, it jumps to 75% accuracy. So there's a certain point after a few epochs, it starts understanding, okay, you want me to be a geometric classifier, and then it starts doing that, and it ends up at 80% accuracy. So it jumps pretty significantly, right, as far as performance, and with just simple basic training. And then you can see the outputs here significantly improve off of the simple test that I give it here. And then within this architecture, I can already tell you up front, this isn't the optimal architecture for this, right? I don't know what the optimal architecture is for a geometry awareness function, because this is the first geometry awareness function that I'm aware of that's been built. So I don't know how to optimize it, but I know that this isn't 100% built optimally as is, but it works, and that's what I'm showcasing here. So let's dive into this. And the bottom line, and the first place I want to start with this discussion is I want people to understand why I keep having these discussions and why I keep talking about this and geometric spaces very specifically. And I have gotten, I think, better at trying to explain this. So we, as people, exist in a physical realm, right? We're physical in a physical environment. And then we can imagine other environments that exist, right? So we would have the physical universe and the imaginary universe. So that's two universes. But the imaginary universe isn't just the imaginary universe. When we put math into the imaginary universe, it can be different universes depending on the shape. The shape of the universe itself changes the math, which then creates sub-universes within this imaginary space. So in physical space, we can still have one physical dimension, but in imaginary space, we can have imaginary space that is split up and has sub-universes. And then those sub-universes in this instance would be related to geometry, as I've been talking about before extensively, right? So depending on if you bend the shape, if there's curvature in the space, then those would change the imaginary space. Those would create different imaginary universes, different mathematical universes. And within these different mathematical universes, they each have different properties. The laws of physics are different. The mathematical equations that you use, the functions that you use are different. If you run the same function in one of these subuniverses, you can get different outputs depending on the function. And you can get the same output across all of them too, right? It's kind of weird that way. But so there's some overlap and there's some not overlap. But there are four distinct sub-universes. And then as a human, as a person that exists in the physical realm, none of this ever matters, right? And then 90% of the time and 90% of your life, none of this matters, because if you use imaginary space, we all default to kind of what we were taught in elementary school, which is shapes, right? And then we think of these shapes in 2D forms, just because we were taught a triangle and a square before we were taught like a sphere and a 3D rectangle, right? And then so our default is to think of these things in 2D space, in Euclidean geometric space. But if you are an entity that happens to exist in these mathematical realms, then the differences between these mathematical realms are extremely important to you. because you can literally you literally have to deal with the differences, right? As an AI entity, as a neural network, it's essentially its environment is geometry, right? And then so if there are four different neighborhoods that exist within geometry and the rules are different in each of the individual neighborhoods, then that's kind of important for the LLM model, right? But we keep putting the LM model and giving it the rules of this one neighborhood, of this neighborhood, this Euclidean neighborhood, right? Because it's the neighborhood that we continually go back to. But there are instances where it would want to be in this neighborhood, or in this neighborhood, or in this neighborhood. And then so we want to be able to just easily dissect that. And then this is my very first attempt at doing that. Essentially going through here. I think Gemini actually does a really good job of summarizing honestly what this code is and how it works, right? So essentially there's the geometric embedders, so hyperbolic, spherical, and fractal, right? And those go through and then they determine, and they essentially each one of them is a calculation, and then the calculation determines which one of these models fits the particular data the best, and then it gives it a score. And then so you have your geometry classification, and then based off of that, the model can then embed and create embeddings based off of the specific geometry. So for example, if we take a sentence, the cat sat on the mat, and then I embed that into Euclidean space, the embeddings are going to be different than if I embed it into hyperbolic space. So again, you start to see why this is important, right? If you only give it one embeddings all the time and one answer all the time, that's all you're going to get is one answer and one output. And but there's actually four. So just I'm trying to highlight this as much as I can. And so when diving deeper into the key concepts of this, essentially it's just geometric deep learning, adaptive representations, and then I'm representing it via graphs. Very simple, right? Is kind of all that is going on here within this code. And then again, within the secondary layer, all I do here within this is I'm just adding a training layer onto this code and going through. I guess highlighting the last thing to highlight and to point out within this particular video is like what leads me to this specific train of thought, right? To this geometric embedder. And so I start here. And then so this paper, softmax is not enough for sharp out of distribution, which was published on October 7th by Google DeepMind. It's a very interesting paper. And then so Google, it's interesting to note that Google are the creators of attention, right? And then if you, most people probably don't know this, but so softmax is a integral part of attention. Like it's a attention introduced softmax, and then softmax inherently operates within Euclidean space and Euclidean space only. And then so as people are going through, they're finding limitations within softmax. And then so just hypothetically, I go through, what do I think? I think that 70% of the limitations that people are finding within softmax and that are pointed out within this paper, the problems within this paper are tied to this, right? And then so that gets you like, where do I get from that to here? Very simply, right? So this paper is saying that softmax is bad, that there's problems with softmax, that there's problems with the attention mechanism, that there's problems with transformers, but that they're not inherent problems. We can fix these problems. But so what is the problem, right? This is the problem. Softmax is the problem. The problem with softmax is it inherently operates only within this space and it ignores these spaces. And then to me, through all of my research that I keep finding, I keep going back to this and finding that if you do that, if you only play in this space and you ignore these three, then bad things happen to happen. And then it just keeps getting hooked up again and again, right? So just coincidental there. I'm not trying to prove that out to you, but let's prove it the opposite way then. So let's see if we include these, does it get better? And it does. And then that's what we're dealing with here, right? So I'm just giving you another avenue to include this within it. You can add your own, rather than, you can utilize this to replace the softmax function. That's the where I'm getting at within this, right? And so this is step one within that, is to do this, to replace the softmax function, I put this geometry awareness function to operate, and it's kind of my step one, and I'll go from there and build it out. But so I want to make this video, showcase this. Hopefully, if you're into like graph neural networks, those types of things, this should be really up your alley, and hopefully this is useful for you. I'll make this, I'll put this into GitHub as well, but then I'll leave a link to this collab in the video. If you like this type of content, please like and subscribe. Thank you very much.